Hello, welcome back to our course on advanced quantum mechanics. This is lecture 14. In our previous lecture, we covered the spectral theorem for self-adjoint operators. It said that if an operator f hat is self-adjoint, which is to say if it acts the same way as its adjoint, and if the domain of f hat is the same as the domain of its adjoint, then there exists an eigenbasis. There exists a basis of vectors, Fn, which is discretely labeled, with n coming from some discrete set of labels, and possibly also some continuously labeled set of eigenvectors where the labels f are from some continuous set of labels. So some interval or maybe several intervals of the real line. This is the generic case. In practice, some self-adjoint operators only have this discretely labeled part, and some have only this continuously labeled part. Now, either way, for a self-adjoint operator, these are eigenvectors, either proper ones, which means normalizable, or improper ones, or approximate ones, which means not normalizable. So f hat acting on one of those proper eigenvectors produces the eigenvalue times the eigenvector. And similarly here, the self-adjoint operator acting on one of the improper or approximate eigenvectors produces the eigenvalue times the approximate eigenvector. And this is one of the main conclusions of the spectral theorem for self-adjoint operators, we have that these eigenvectors are orthonormal or can be orthonormalized. See, they may not be normal to start with, you may have to make them normal. So when you take any two of these eigenvectors from the discretely labeled set corresponding to the point spectrum, then you find that their overlap is a Kronecker delta, so they're orthonormalized. If you take any two of the continuously labeled set of approximate eigenvectors, then their overlap is a Dirac delta of f minus f tilde, and while this is ordinary normalization, this is called continuum normalization. What if we calculate the overlap of a vector taken from the discrete part of the spectrum and an eigenvector or an approximate eigenvector taken from the continuous part of the spectrum? Well, their overlap is always zero, because they're never the same. Okay. And finally, we also noticed that all the eigenvalues, or actually the entire spectrum of a self-adjoint operator, consists of real numbers. Now, I'd like to add that there's a spectral theorem also for unitary operators. Similarly, there exists a theorem, a spectral theorem, for unitary operators. Sometimes they're also called just unitary or unitaries. And it says pretty much the same thing. Let me just remind you. Recall, u hat dagger is equal to u hat inverse, means u hat is unitary. Okay. So what the theorem says theorem is as above. There's a continuous spectrum, there is a discretely labeled spectrum, that is to say there's a continuous spectrum and a point spectrum, and everything is the same as above with the normalizability of these eigenvectors and so on, except one difference, except that for the eigenvector equations, u hat acting on an eigenvalue equal to u, if u is in the continuous spectrum, or u hat un if it's in a part of a discrete spectrum, of the point spectrum, un, we have that un star equal to 1 over un because of this, as you can easily convince yourself. We must have this condition, and for the continuous part of the spectrum, of course, similarly, any approximate eigenvalue coming from a continuous part of the spectrum must obey that u star is 1 over u. But what does it mean? It means that un star un is equal to 1, and similarly, u star u equal to 1. And this means that, therefore, the spectrum of every unitary u hat is on the unit circle in the complex plane. So each eigenvalue, proper or improper, normalizable, corresponding to a normalizable eigenvector or a non-normalizable eigenvector, each number in the spectrum is a complex number whose modulus is 1. Right? We have that here. Modulus is 1. Okay, so we have a spectral theorem for self-adjoint operators. We have a spectral theorem for unitary operators. Is that it? No, actually, there is the most general spectral theorem. Spectral theorem. And the spectral theorems for unitary and self-adjoint operators are just a special case of this one. So in order to formulate this one, we need to first make a definition. We call an operator Q hat normal if it obeys that it commutes with its adjoint. If Q hat dagger is equal to Q hat dagger Q hat, and of course they have to act on the same domain. So D Q hat dagger must be the domain of the Q hat dagger Q hat. Okay, so this is the condition for an operator to be called a normal operator. And now the general spectral theorem says the general spectral theorem, it says that assume that Q hat is a normal operator, then it possesses an eigenbasis consisting of eigenvectors Qn that might be discretely labeled, and possibly also eigenvectors Q that would be continuously labeled, Q element J and Qn element M. And the Qn and Q can take arbitrary values in C. Or possesses an orthonormal eigenbasis. That's very important. And so I should put this in brackets, continuum. A continuum orthonormal eigenbasis. I'm putting that in brackets because you know the drill now. If the eigenvectors are normalizable, then we have orthonormality, and if they are not normalizable, then we have continuums orthonormality with the Dirac delta replacing the Kronecker delta. So it's all very much similar to the spectral theorem for self-adjoint operators and the spectral theorem for unitary operators. Let's quickly check something here, namely, assume that U hat dagger equal to U hat inverse. Does that mean that U hat is normal? And let you figure it out. Actually, I tell you, yes, it means that, but I let you figure out why that is the case. And similarly, self-adjoint operators, they obviously commute with the adjoint because they are their adjoint, right? So assume X hat, no, not X, we call it F. Assume F hat equal to F hat dagger. Well, then F hat dagger is equal to F hat, which is F hat dagger F hat. Therefore, F hat is normal. Now, can we cook up a normal operator that is not unitary and not self-adjoint, whose spectrum is not real and not on the unit circle? Yeah, easy. Example, let's say we define an operator Q hat in a basis Bn. So let this be a countable basis in our separable Hilbert space. And then we define Q hat in a basis be defined as Q hat, and then I'm giving the matrix elements Bn, Bm equal to Qn delta Nm with Qn equal to, well, as we run through the various n's, we get, let's say this is 3, 7i, 5, 8, and then 1, 1, 1 forever, right? So in this case, we have that in the Bn basis, we have that Q hat Nm is given by the matrix, which is diagonal and has entries 3, 7i, 5, 8, and then only ones. Forever ones, ones, ones. Okay, n comma m. Is this a normal matrix? Well, yes, it's diagonal. And therefore, its Hermitian conjugate is diagonal. The only thing that changes here is that the 7i becomes minus 7i when you complex conjugate it. So there is an I here. Right, and two diagonal matrices, of course, always commute. So clearly, is normal. Is normal because diagonal. Yeah. So what we see here is something very important. Every diagonal matrix is normal. What the spectral theorem says is that every normal matrix is also diagonal in a suitable basis. You see, if, for example, we take our Q hat, which is diagonal in this basis, and rewrite the Q hat, an abstract operator, this thing, let's say we rewrite this in a different basis, in a completely different basis, well, then the Q hat is not going to be a diagonal matrix, it's going to be some wild matrix. But it's still normal, because if an operator is normal in one basis, it's normal in every basis, right? Because normality is not something that's basis dependent. It's a property of the operator itself. Does it or does it not commute with its adjoint? So we could easily generate non-trivial examples of normal operators by simply taking this normal operator here and rewriting it in a funny basis. Okay, so the overall story here is that diagonal matrices are normal. But, and that's non-trivial, I mean, it's trivial to see that diagonal matrices are normal. But what's non-trivial is the spectral theorem, which says that normal operators are always diagonal in a suitable basis. So normality is the same thing as saying that it's diagonal in a suitable basis. This is useful to know. Now, let me give you an example of an operator that is not normal, because all of these things do come up in practice. An example, remember the operator A, which in a basis had the form, so its matrix elements in the Bn basis, for example, where 0, 0, 0, etc. And then here we had square root of 1, square root of 2 factorial, and square root of 3 factorial, etc. Zeros here, zeros there. No, actually without the factorial. So this matrix, is it normal? Well, remember, we have that A dagger minus A dagger A was the identity. So therefore, this is not equal to 0, and therefore A is not normal. Isn't that curious? Because if you remember from one of the exercises, recall, and that was an exercise, recall that there exist eigenvectors of A. the so-called coherent states. Namely, we found we found vectors alpha obeying A alpha equal to alpha alpha. And we found this for all eigenvalues alpha in the complex numbers. Isn't that curious? Doesn't that contradict what I just said? I said that the normal operators are the ones that can be diagonalized, and the diagonal ones are the ones that are normal. There doesn't seem to be any wiggle room here. And this looks like we diagonalized the operator A. Or did we? You see, we didn't. Because for A to be diagonalized in the basis of the alphas would have to be orthogonal, but they're not. See? So, however, the alpha do not form an orthonormal basis. We have that when you calculate it, alpha tilde is not equal to delta of alpha minus alpha tilde. So therefore, this is not a contradiction to the spectral theorem. The spectral theorem says that if the operator is normal, then it has an eigenbasis that is also normal. Our operator A is not normal. It has an eigenbasis, but that eigenbasis is not also normal. So to take away from this is that operators in quantum mechanics can have eigenbases even if they're not normal, even if they're not unitary, even if they're not self-adjoint. But then we have to expect that something's wrong with that eigenbasis, namely that these vectors are not orthogonal. Other vectors, other operators that are non-normal may have no eigenvectors whatsoever. This one has a lot of them. So we have to take the spectral theorem very literally. All the conditions need to be obeyed for all the consequences to follow. Okay, now let's switch gears and apply all of that machinery that we developed over the past 2 lectures to calculate the actual spectrum and eigenbasis of an interesting operator, or several of them actually. Namely, let's calculate the eigenbasis of the position operator. Remember what we do know about the position operator so far. We found early on in this course a representation of the position operator, and it looked like this. It was given as a matrix with coefficients n, x, and m, given by L times, and then this matrix. On the diagonal, zeros, and then on the off diagonal, we had square root of 1, square root of 2, square root of 3, square root of 4, and also here square root of 1, square root of 2, square root of 3, square root of 4, etc. forever. Remember, it was L times A plus A dagger. Okay, and so here we have the n, m's matrix element. So the n, m's matrix element of this matrix is what we call the x hat nm. And this obviously is in a basis. And we used to call this basis the basis of the BM, but for reasons of convenience later on, let us call the basis En. So let us call the underlying choice of bases the En, n equals 0 to infinity basis. So we will count from 0, not from 1, and we will call these eigenvectors the En. Again, it will be, we do that because it will become convenient later on. But what it also means is that this element up here in the matrix, the top left element, is actually the 0, 0th element. And that would be the 1, 0th and the 0 first element, etc. Right? So we start counting now from n equals 0. Well, then if we call the basis here the basis of the En, then let us spell out technically what it is that we just wrote down. What we just wrote down is that the XNM are actually the matrix elements En, X hat, Em, right? So this equation here is really this one. It's really this, okay? So what we're saying is that, you know, these matrix elements are that. Now, that's useful because having identified what the matrix elements are of the abstract operator X in the En basis, we can now write down this abstract operator X in the En basis. So we can now write, therefore, the abstract position operator is given by sum over n and m, and then we have these coefficients x hen x. Oh, let's write it like this. Let me remind you just to make sure. Let's just rewrite it quickly. So what we have is that this is En. Sorry, that's not what I meant to do. Okay, so this is 1 x hat 1 equal to sum over n m, and then we have a resolution of the identity En x hat, another resolution of the identity Em. Now this is of course what we wrote is XNM. So therefore we have that x hat is equal to sum over n and m, and then the x hat nm, and these matrix elements are taken from that matrix up here, and then we have the basis vectors here, En, Em, and those guys are just numbers. The x hat nm are just numbers. So now we have an abstract expression, a concrete expression for the abstract operator x hat. And we want to find out how can we diagonalize that operator? How can we calculate its eigenvectors and eigenvalues? See, obviously, the position operator is not diagonal in this basis. These matrix elements don't come from a diagonal matrix. This matrix up here is not diagonal. Now, before we find the eigenbasis of the position operator, let's just take a moment and think about, well, the fact that the EM basis is an orthonormal basis. So therefore, it's the eigenbasis to some self-adjoint operator. Can we find a self-adjoint operator of which the EMs are an eigenbasis? Can we find a self-adjoint operator that is diagonal in the EM basis? Well, the position operator is not, but maybe we can find another operator that is diagonal in that basis. So can we find, I put here exercise. Can we find an operator that is diagonal in the EN basis? Well, remember, we had this operator. We had A with matrix elements A and M equal to 0, 0, 0, 0, and so on, and then square root 1, square root 2, square root 3 in the EN bases. Now define an operator n hat, which is A dagger A, and then exercise show that n hat is diagonal in the basis of the EN with well, well, with spectrum, let me just give it away, with the spectrum En equal to 0, 1, 2, 3, etc. Now, this is all good and fine, but didn't we want to find the eigenbasis of the position operator? So let's get back to that. So find the eigenbasis of x hat. Well, how do we do that? Well, obviously, we need to solve the eigenvalue equation. We need to solve x hat acting on x equal to xx. Well, why don't we just solve that? You see, it's a very abstract equation. In order to solve it, it's useful to choose a basis, because where can we go from just this if we don't choose a basis? So, remember, these you have to find out. What are they? And what are these eigenvalues? Now I'll show you how to calculate these eigenvectors and eigenvalues, and therefore the spectrum, from scratch, using a basis. Once in a lifetime, one should do this for the position operator. And then you know what it is. You know the eigenvectors, you know the spectrum, and so on. But it's good to do this also because the very same techniques that we are now going to apply are used in practice to find the eigenvectors and eigenbases to observables where it's not previously known. It happens all the time in atomic physics, in molecular physics, chemistry, and also in quantum information theory, that we have to diagonalize the one or the other operator, and this is how you do it. So choose choose the basis, namely let's say we choose the En basis, and we do that because we already know something about the En basis. Then the first step will be we apply one of these basis vectors from the left. Because this is a vector equation up here, and it's better to work with numbers. So we turn this into a number equation by putting a bra vector from the left. Then we obtain, namely, that En x hat x is equal to x En x, right? This little x is just a number after all, so we can pull this out. Okay, and now we put here an identity operator and insert the resolution of the identity. Remember, we've done this before in the abstract. Now we do it for a concrete example. So we obtain that the sum over the En x hat Em x equal to x En x. What do we have here? Well, what we have here is these are numbers that we know. These are the x hat n m from the matrix that we considered above, right? So these are simply these numbers here. We know them. What we do not know are these numbers here. What are they? They are to be determined wave function of oh, what? Wave function of a position eigenvector in the En basis. And this is a to be determined, to be found eigenvalue. We only know it's going to be real because our X is self-adjoint. So we have an equation here with unknowns and with knowns. So these matrix elements are known. You can view this literally as a matrix, and this as a column vector, and here's a column vector again, and here's an eigenvalue. So we have a very concrete equation to solve here. Now, this is a vector equation, right? Here we have a column vector, and here we have a column vector on which a matrix acts. So on the left, we also have a column vector, and on the right. And we can go through the various components of this vector equation here. I mean, it's actually numbers, right? But we have the coefficients arranged of an abstract vector in this column vector. Okay, so what do we obtain? For the n equals 0 component, so if we choose in this equation, remember in this equation we are summing over m, but n is fixed from the outside. If we choose n equals 0, then the equation that we obtain here is that L times square root of 1, I'm using that we know what these coefficients are. So it's L square root of 1, and then it's E1 x is equal to x times E0 x. And I invite you to check that for yourself. Just take the matrix, take the unknown column vector, apply the matrix to the unknown column vector, and then look at the very first entry of the column vector equation here. That's this one. Now the second component of this column vector equation looks like this. N equal 1 is L square root of 1, and then E naught x equal to, no, not equal to, but plus L square root of 2, and then E2 x is equal to x E1 x. And okay, and I'll write down one more equation so that we see the pattern. N equal 2, we have L square root of 2, and then we have E1 x plus L square root of 3. E3 x equal to x E2 x. Right, so on the right-hand side, it's clear. We have the 0 component of our column vector, then we have the 1 component of the column vector, then we have the 2 component, and down here we are going to have the 3rd, the 4th, the 5th component. On the left-hand side, we had this matrix here, this matrix acting, right? And you see, if you take the column vector and and apply it to this matrix, then the first term is going to get just 1 contribution, and the next ones are getting 2 contributions, 2 contributions, 2 contributions, etc. That's why down here we have that the very first line has only one term on the left, but the second term has already 2. In the second line we have 2 contributions, and then 2 contributions, and so on, always 2 contributions, and they're always going to be with 1 gap in between. There's E1 and E3, here E0, E2. The next line would be an E2, E4, etc. The point is, what we really need to read from this is that we can solve that. Remember, what we need to determine is, what are these coefficients E naught x? What is, in other words, the wave function of the position eigenvector in the E naught basis? We need to find all of those x E naught, x E1, x E2, x E3, etc. We need to determine them all. It might look difficult, but it's actually easy. Well, it's easy to work it out numerically. To get a closed form is a whole different story. But what we need to observe here is that it's conceptually easy. Namely, pick some non-zero value for E naught x. Say r equal to E naught x. Then all Enx follow. Why is that? Imagine we have E naught x fixed to be the number r. Well, then we immediately get what E1x is, right? I mean, remember, first of all, we choose an eigenvalue x, some real number. We choose our first component of the eigenvector to be r, and then we get E1x right away from the first equation. At this point, we have E naught x and we have E1x. Looking at the second equation, we see that having E naught x and having E1x allows us to solve for E2x. Great, now we have E naught x, E1x, E2x. And with the third equation, we get now E3x. And it goes on like that. So recursively, we can get the solution here. Therefore, can solve recursively for all x in R. Because this works no matter what eigenvalue we tried. You can choose 5 and this recursion will work. You can choose 1,000,000 and it will work. It will always work. And from that, we can conclude something very important. Namely, we can conclude that the spectrum of the position operator has to be the real line. Actually, the recursion can be solved entirely. Actually, with some hard work, the recursion can be solved in closed form. And what we obtain is that, and I will save us the trouble of going through the derivation of this, but what we obtain is that the solution to the recursion is given by e to the power minus x squared, x being the eigenvalue that we pick. And then this is the this is the wave function. So this is going to be square root of pi, 2 to the power n factorial, and then the so-called Hamid functions, x divided by square root of 2l. Here, Hn is the nth Hamid polynomial. And the nth Hamid polynomial is defined in the following way. Hn of its argument z, in our case z is x divided by square root of 2 times l. This is by definition minus 1 to the power n e to the power z squared, the nth derivative of e to the power minus z squared. This is a polynomial, even though there are these exponentials in there. Why is that? Well, if you differentiate n times this function here, you get a polynomial down. But it's multiplied with e to the power minus z squared. And that e to the power minus z squared persists after you're done with the differentiation. And then it will cancel itself with e to the power z squared. So overall, this is always just a polynomial. Now, what value should we choose for R, though? What should we choose for that value? You know, that's the value that that determines what this wave function of the position eigenstate in the En basis takes for the first coefficient. Right? This is x E naught determining. Now, of course, you want to choose R so that the x are orthonormal. However, remember the spectrum of our position operator we now know is continuous, and we know from the spectral theorem that means that the x are not normalizable. They can only be continuum normalized. Now, let me put it this way. Since the spectrum of x hat is the real line, the spectral theorem implies that the x are improper or non-normalizable or approximate eigenvectors. The x are in R are approximate eigenvectors. Eigenvectors that must be continuum normalized. Normalized. And indeed, we can do this, indeed, with choosing R equal 1, we obtain, one can show, but we won't go through the trouble for this, one can show, because that trouble would be just pure math and not physics, not mathematical physics, so we obtain, because one can show, that the sum over n equals 0 to infinity of the x en x from above. Remember, this is this thing with the Hamid polynomials and so on. This, which is of course, oh sorry, I put a tilde here, which is of course this, is indeed the delta of x minus x tilde. Okay? So this means we have now found what the wave function is of the position eigenvectors in the En bases. Namely, to be explicit here, this is the position eigenfunction for R equal 1. This is the wave function of a position eigenvector in the basis of the En. It's exactly given by this thing here. Now there is a beautiful corollary, it's a beautiful consequence of having obtained that result. Corollary. Remember what we know from the harmonic oscillator. H hat equal to p hat squared over 2m plus m omega squared half x hat squared. In an exercise, we found something that's very useful, namely that h hat can be written as h bar omega a dagger a plus 1/2. Now we know because n hat is a dagger a, and the spectrum of n hat is 1, 2, 3, sorry, it's 0, 1, 2, 3, etc. Now we know because of this that the Hamiltonian of the harmonic oscillator can also be written as h bar omega n hat plus 1/2. And just to be completely explicit about this, Sorry about that, the software crashed again. Okay, so we found in this exercise that the Hamiltonian can be written in this form. Actually, I should add here, we found that the Hamiltonian can be written in this form if we choose that L is equal to 2m omega to the power of -1/2. Right, and since we now also know that the n operator is A dagger A and has the spectrum 0, 1, 2, 3, etc., we have that the Hamiltonian, oh, I wanted to write, that's when the computer crashed. I wanted to write here that we can put the identity operator in here, right? So it's A dagger A plus 1. So what we have is that A dagger A plus 1/2 times 1. So we have that the Hamiltonian can be written, and I will write it here as a matrix with entries n and m, can be written as a matrix which has these entries. H bar omega from here, and then we know that A dagger A is diagonal with eigenvalues 0, 1, 2, 3, etc. And then we add 1/2 here. So this is 1/2, and then 3/2, and then 5/2, and then 7/2, etc., and 0 and 0. What this means is that if we if we choose to look at a harmonic oscillator and we choose the free parameter L that we had so far to match 2m omega to the power of -1/2 of that harmonic oscillator, then we have that the Hamiltonian of the harmonic oscillator is actually diagonal in the En basis, i.e. then the basis of the En is Eigen Basis of our harmonic oscillator. If we chose a different harmonic oscillator with a different frequency, or we chose our parameter L, which after all was arbitrary, if we choose that parameter differently, well, then the Hamiltonian is not going to be diagonal in the En basis. So what we have as a nice side effect is that we happened to work with the eigenbasis of a harmonic oscillator, of a particular harmonic oscillator. The En basis is the eigenbasis to a particular harmonic oscillator. We can also say that the spectrum of H hat, which is the spectrum of the operator p hat squared over 2m plus m omega squared half x hat squared is equal to h bar omega half and h bar omega 3/2 and then 5/2 h bar omega, etc. And nicely, this is a basis independent statement here, right? This is basis independent. So even though we did work in a particular basis, the result, namely the spectrum, is of course basis independent. No, the spectrum consists of the eigenvalues, and eigenvalues are eigenvalues. They are scalars, not basis dependent. Now, finally, we come to another beautiful observation here. You see, while we are working with the harmonic oscillator, while we are considering the harmonic oscillator, let us also ask, what are the what are the wave functions? What are the wave functions of the eigenstates of this harmonic oscillator in the x basis. Remember, we calculated the x basis. We can now use the x basis in the x basis. So what are we talking about? Remember that the harmonic oscillator has discrete energy levels we just discovered. They are h bar omega times 1/2, 3/2, 5/2, 7/2, etc. And the corresponding energy eigenstates, Hamiltonian eigenstates, are called En. So E0 is the ground state, E1 is the first excited state, etc. And we are asking, this is the state, let's say the nth excited state. What is its wave function in the position eigenbasis? This is traditionally written as psi n of x, a position wave function. It's the wave function of the nth excited state of the harmonic oscillator in the position basis. This is what we need to calculate. Now, what is this? Let's recall we already calculated Enx. Namely, we already calculated what the wave function of a position eigenvector is in the En basis. This was this complicated expression with the Hermite functions. This we have explicitly as a function of x, the eigenvalue of position, and as a function of n that labels this basis. We already have that. But you see, this is a real number every time. It just came out this way, that all of these are real. And therefore, we have that psi n of x, which is x En. I'm just rewriting what we had up here. This is the desired wave function, the position wave function of the nth excited state of the harmonic oscillator. This is Enx star, because remember, AB equal to BA star, always in our Hilbert spaces. If you turn around the argument, then you get to pick up a complex conjugation. But this is equal to Enx, because it happens to be real, but even if it were not real, we could still handle it. And this is, from what we had calculated earlier, this is actually e to the power minus x squared divided by 4l squared divided by square root of pi 2 to the power of n factorial times the Hermite polynomial of x divided by square root of 2l. So therefore, by calculating the wave function of a position eigenstate in the energy eigenbasis of the harmonic oscillator, we inadvertently, without intending to, we also happen to calculate the position wave function of the nth excited state. This you can keep in mind as a generally useful tool whenever you calculate the basis vector, one set of basis vectors in terms of the other set of the basis vectors, let's say the eigenbasis of one operator, in terms of the eigenbasis of another operator, as we did here, then you always get mutual wave functions. Like here, the position wave function in the energy basis, but you at the same time get the energy eigenfunctions in the position basis. Just by switching the arguments around in the overlap calculation, possibly with a complex conjugation, but that's easy. Okay, this is as far as we got today. I wish you a nice reading week. I will communicate with you via email.